And now Pratik Dabhade is going to talk us about VLBI scale probing of radio galaxies.
Okay, so hi everyone, I'm Pratik. I'm new to the PhD campaign. I'm coming from low frequencies, into high frequencies. So some of you must have heard part of this talk last year in November. So I'll build on those and try to put some ideas and get some feedback from you all. So just a primer, I mean, everybody knows what are radio galaxies. We have various shapes and sizes for that. But just to focus on the giants one. So just to give you a perspective, we need to stack a lot of independent galaxies to make that megaparsec scale. They're really, really huge. So these were found in the 1970s with Westerbork, and ever since there have been multiple efforts to look for them because they are not so they're quite rare compared to the normal size galaxy. So this is just a comparison of how the biggest ones are with respect to each other. 1987 is when they got here. Coming to the main topic. So we defined the total overall size of the giants to be 700 kiloparsec and bigger. We measure the size from end to end, the hotspots. And this is like something which we knew until 2016, where only about 300 or so sources were known, and mainly where radio studies were carried out in not material kind of studies, and they are very good labs for studying astronomical jets because they have kiloparsec long jets propagation. So why do we study them? Because there are some open problems. Firstly, we don't really understand fully that why they are so big, what makes them grow to such large scale, how are they formed. I mean, in principle, they are radio galaxies, are very much the same, but there is something special happening there, which is leading them to grow in such large sizes. So we want to understand that. We want to also understand how they contribute to other processes, large scale processes. So there have been propositions that they are probably just old galaxies which have grown large over a period of time, or perhaps there is some sort of restarted activity on a shorter scale which we can't observe, and that's why they are growing bigger and bigger. And we can also study a lot of LSD things. So two main models which have been proposed are these, that they perhaps host very powerful radio region, or they grow just in very sparse environment allowing them to. Or it's probably a combination of two. So we need to, but this was not known what could be the actual cause for this. So we needed to find more of these giants and do this material and environmental study to try and probe these questions. So it's obvious new sensitive surveys in radio optical are going to find more. That's what we did. And then we needed to do all these kind of things to understand their properties better. So I'll just go through what work has been done in the last 4-5 years by me and my group. So we started this project called Thalia. It's quite coincidence that we are in the same thing. It stands for search and analysis. So it was started back in 2016. So we set out this set of goals that we need to find more of these giants from existing survey. We need to know how much, what fraction of these are known in the literature. Can we find more? Use all sort of optical multivariate data to get their properties, platform mass, ratios and stuff. And then do a systematic radio survey to understand their properties which are complete. So this is the status until 2016. So first task was quite tedious because we wanted to go through a lot of literature to understand, and people didn't follow same nomenclature. So it took quite a time to understand what is the exact number, and we did that and we made this catalog. So we also carried out we also carried out searches from new surveys like the low frequency sky survey, and found big samples like these. and then almost double the population, and we produced this catalog of 20 giants. So this until 2016 only 300 or so, and of which only 50 was studied in the radio, frequency and stuff. And now we have a big catalog. Now we could really go into more specific science. So we computed all these properties using existing archival data from various surveys from optical, radio, infrared, and we also tried to do a comparison with the ones hosted by Quasars and the ones hosted by this. This is just to give you the redshift range of these objects. So this was the black hole mass and interpretation mainly done using the O3 line and the M sigma relation velocity dispersion of cases. And we try to show that it's not very different for radio galaxies and giant. Of course, these are not the final numbers. We need to do follow up some of them, the potential ones which are really big with the high resolution IFU kind of observations to determine the exact accurate.
How did you measure the mass?
So M sigma relation, we have velocities from the so that's the, but this was the first step. So and we also tried to show some jet disk connection. We estimated the jet power from 150 megahertz plus. The correlation I tried to see. So there seems to be a correlation like it has been shown in literature. And we just tried to play around and see what kind of spin we get. Because here we assume the maximum magnetic field. We just wanted to see how do they compare. Of course, there are a lot of assumptions goes into it, but we just tried to show, and surprisingly we found it to be very low comparatively. Perhaps it's spinning down over a period of time, but that's something which we have to work towards in the future. So this is just a summary of what results we have tried to obtain and what is in preparation. And the summary is that they are not as rare as previously thought. They do grow in denser environment because we found quite a lot of them in clusters hosted by BCGs. Their agents have both low or high accretion mode. So we thought it's going to favor one mode, but that's not the case. The black hole masses came out to be very similar. And in speculations, that is something which we are working on because they require really a lot of multi-frequency data to obtain those values. So you all are familiar with this kind of images and the famous images. So what I'm trying to say is that we have explored the kiloparsec, megaparsec scale with meter centimeter wave, and now it's time for us to probe the parsec scale, the core, the jet at 7 millimeter wave, and perhaps we could do it with ngEHT one day. So first step would be to look at the VLBI. So this is just to show you that firstly the giants were known very less number. So obviously there's follow-up studies with VLBI were quite few. So there are very hardly 10 or so sources in the literature which have been studied VLBI in the past 3 decades or so. They're quite valuable because they tell us if there is a restarted activity going on, how the jets go misaligned with respect to large scale jets. We can try and estimate the inclination angle with respect to us, and the polarization properties. There is some contrasting results which have been obtained and worked out. And so the main thing was to get try and understand what people have done. And so it's expected that since these radio galaxy giants are so big, they are not very too much inclined towards on the plane of the sky. But contrary to that, we didn't get those high values. We didn't the literature. So, but as you can see, this was done for very few sources. So, thanks to the last meeting I could attend before the pandemic, the Jets meeting in Manchester, where we ran into Leonard Petrov, who was very interested in this, and we started this campaign with him of using VLBA to probe the course. And we wanted to know what kind of properties these have at really small scales. So this was observed somewhere found from the archive. Then I had to go and finish my PhD, so I couldn't look at it. And very recently, I could take up the work. And so this is just very preliminary results. I'm just showing you some very interesting sources which tend to show jet structure or some knots, perhaps. But yeah, I need your inputs to figure this out completely. So it was mainly with S and X band, and some had K and U bands with VR second resolution. And I quickly tried to get the spectral index of these four components, and they're expected to be flat, but this was quite a few of them show very steep. So perhaps there is unresolved structure and possibility of restarted activity. So that's very clearly standing out here. So that's something which is interesting to look at now. Maybe that's one sign in the giants that's what makes them large. There is a renewed activity on a shorter time scale. So that's my pitch that why ngEHT, why, because these are the extreme end of radio galaxies or radio quasars. It gives us a chance to explore something new. I've been piecing trying to collect the missing pieces from very low frequencies now, and now trying to with the high frequency. That's how I think all the science goes, and we can get better constraints on various things. The way forward is that I have to complete this project with the VLBA, see what kind of properties we have, compare it with already existing literature, what if there is any difference or similarity, and then probably check with these database. Some of them will be there possibly, and yeah, that's and the second last one is something which I'm trying to do with various collaborators in France, trying to get very accurate pass estimation so that we know what kind of vector we are doing. So yeah, in the end we can choose the biggest, brightest, and the closest. So yeah, solutions are welcome. Thank you.
Questions?
Yeah. So what fraction of these sources are really nearby? This is one of them, right?
Yes. So I think the lowest redshift. I don't know the number in university distance, but I think the lowest redshift is about 0.03.
So when that one would be done within the ngEHT.
So their lowest flux at X band is about 30 milliamps. But again, we'll find more because there have been a lot of new additions to the giant catalog, and there's ongoing surveys with all sort of VLBA experiments, so that will definitely do something.
So and you expect obviously an overlap with the ether survey?
Yes, because yesterday I heard his talk and he mentioned SDS in the database. Much of this comes from
Patro?
Curious how many of these have a detectable core on the parsec scale.
So about 90% of them show cores. I did not know this until VLSS came. When VLSS came, I tried to see, and 90% of the show 3 gigahertz core.
Yeah, that's great.
Yeah.
Sarah?
Yeah, kind of a follow-up. I mean, based on what you know about the inner core, based on the smaller scale, can you say anything about, have you picked up any sort of mismatch in the inferred power from the inner jet to the outer jet? I think that's just a really interesting question, right? Because people are always making assumptions of the power based on these really large scale loads. And of course, you're off of contact, from the core.
So that is something I look into. I want to look into what limited information which I gathered is that in some sources there is a lot of misalignment up to 30 degrees. There is either second scale jets or the kiloparsec scale jets.
So it could be even different methods.
Yeah, or something is happening.
The last one, Diane.
Yeah, you mentioned that there are 225 new detections from ROFR. Yeah, are there any information on higher underwater resolution from the sources? Are there any higher underwater resolution information of these new buffer sources?
Not these new, but from the literature, there are quite a lot of them certain for
Thanks once again, Pratik. And now Professor Matt Lister is going to talk us about multi-frequency MOJAVE time-lapse imaging. Thank you.
So I want to tell you about a little project that we're doing at the Mojave survey. This is a new direction for us because we've added 2 frequencies. And the idea here is kind of as a precursor to what ngEHT might be doing at VLBA. Just want to acknowledge my collaborators in the project. If you don't know what the Mojave acronym here, it's an acronym within an acronym. I just want to acknowledge my funding and supporter of the perfect project. Okay, so as I mentioned, ngEHT, the killer app is going to be time-lapse movies. If you ask people in the public, what's next for ngEHT, they'll say, where's the movie? That's what they want. So the goal is to do this in full polarization. We want multi-frequency. We want to bring everything to bear on things that's close by, AGN, M87, and also Saturday Star, but also Blazars as well. This particular program that we did with Mojave was to look at 25 jets that were transversely resolved, that had high fractional polarization, and were bright enough to be observed at all 3 frequencies, so we get detections. So these objects span a large range of redshift, so from 0.03 to 2.4, and they also span a huge range of expansion speed of the sky. So this is important for checking things like how accurate the epoch to epoch can the VLBA reproduce the actual structure, particularly for these slow moving sources. And we put many of your favorites here, free, we also have a range of the spectral, the low spectral peak and high spectral peak VLBIs in there. Then we got the 2 close by radio galaxies. It looks fine when I prepared it, so okay, so we've got 24 epochs at these 3 frequencies, and we have monthly observing over a 2-year period. And we call this snapshot plus because what we do is we look at the source about 6 to 8 separate scans, depending on the low definition sources get fewer scans. Those are the different hour angles. So it's not a full track coverage. It's you get snapshot coverage like this, and so each of these is a different scan essentially. It really varies by definition. So this is a nearby equatorial source. The VLBA doesn't have a very large north-south coverage. And this is a high definition source, which gives you more uniform coverage. So we cycle through the 3 frequency bands in each scan, and then we allocated the bands because the atmosphere, the systematics, the receiver temperatures are higher at 14 gigahertz, so we took twice as long. That's supposed to be 2 right there at 43 gigahertz compared to 15 gigahertz. So here's just one source epoch. This is a quasar around 17, and gives you an idea of what we can see at 40 gigahertz compared to 50 gigahertz. And in these images, I've got the total intensity on the left with fractional polarization as a false color. And this is the electric vectors here that don't show very well on the screen. But the idea here is that this jet emission is two spectrum. And so as you go to the higher frequencies, you lose the sensitivity to all this outer structure. So this box right here corresponds to what we're seeing for you. And as you notice, the beam gets better. This is the fixed array. And
it's not dual weight.
this is natural weighting. And so for the movies, what we do is we evolve to the new band. We evolve to this beam. Okay, so what do you do with multi-frequency? You can use those maps, but you can also produce spectral index maps and rotation measure maps. Okay, so definition of spectral index here is a log relation, and so you get a flat spectrum core here, a steep spectrum jet. So spectral index down here is what you'd expect, -0.7, -1. And then the rotation measure, this is assuming a lambda squared law. And so what you're seeing here is this plot in radians per meter squared. And so again, there's a gradient in rotation measures. So you can see these what these are. As you go downstream, you get inverted rotation measure. So in this case, we're going negative to positive. Or yeah. Okay, keep on screen. Okay, so I mentioned this as a precursor to what we expected to achieve. So the calibration is very intensive to extend. Okay, so you might think that just registering the sky position for each source epoch would be straightforward. It's not. The reason is that self-calibration, it gets rid of the absolute sky position. It will put the brightest feature of the jet on center. So typically what's done, it's been done in the past, is you use the cross correlation. So you've got the image at 15 gigahertz, you've got one at 24 gigahertz. You say, okay, apply a shift and see what's the minimum there for producing the difference in those two. The problem is that there's a sharp spectral index gradient as you go down the jet. So if you use all the image, you're not going to get the right shift. You have to weight properly, or you have to mask the image. So doing it some sort of simple cross correlation blindly is not going to work. What we found is if you just use the core region where it's unresolved, you put an unresolved core there, you look at the cross correlation to that works the best. It's not perfect, but it's the best one. Also, the shifts between epochs are a problem because the core itself can shift as new features emerge. The brightest centroid of that unresolved core feature moves slightly, and that's enough to actually throw off your spectral index map. So accurate sky registration is going to be an issue. The other is calibration. Okay, so you've got the typical gain errors associated with self-calibration and cleaning. Also, the polarization leakage terms, you can determine those accurately to get accurate view. And we had problems with the VLBA excellent flux states. So it turned out that at 43 gigahertz, there was errors in the pointing of the VLBA antennas, and that was artificially lowering all of the 43 gigahertz fluxes. So we required external calibration from single dish telescope, like MOJAVE and overall, in order to get the absolute calibration. We've also got issues with baseline coverage. So the VLBA is a minimum array of 10 antennas, and if you take away an antenna, there's a real drop off in industry level. Particularly if it's one of the other antennas, like Montana or St. Croix, or even one of the interior ones. So epoch to epoch, you have different baseline coverage. And then finally, there's the electric vector position angle on the sky. There's no good calibrator for that, so you need an external telescope to make the calibration. Okay, so let's move these now. Okay, so this is the one where we've got a very slow jet. So nothing is supposed to be happening in this. So the variations are most likely instrumental. So what we've got here is a simple linear interpolation, pixel across the epochs. The flux density variations in this particular jet are less than 5% over 2 years. Okay, and the measured jet flow in this region is only about 20 microarc seconds per year. So that's 0.03 beams per year. So this is a good test case to see how well from epoch we produce things. You notice there's a lot of variation down in here. This is instabilities in the clean algorithm. You're not sampling the VLBA, it doesn't have a lot of short baselines. And so if there's any variation for epoch on a short baseline coverage, it's going to get reflected in that coverage. This is not working. Oh, maybe this will, okay. Good. Okay, so this is one where it's fast jet. Okay, so this one, it's 18, this is 3.11. It's moving at 1,800 microarc seconds per year. So now we're talking 3 meters. And notice there's a lot going on in total intensity, which is the dark contours here. There's a lot going on in fraction polarization. And watching here, there's a lot going on in linear polarization. Too bad I can't remember this in my own. Okay, so down in here, these polarization variations are happening way faster than the total intensity. You'll also see differences in quality from epoch to epoch due to failures. So for EHT, there needs to be, ngEHT, there needs to be some redundancy built in to be able to handle. You want fidelity from epoch to epoch. Okay, so this is an animated GIF where it's not interpolated between the images. These are the spectral index. So this is useful for seeing whether from epoch to epoch you're seeing the same spectral index structure. So this plot right here is this pixel. So we have 3 frequencies. And you can see some epochs of 40 gigahertz are low. There's some variation, and the big question here is how much of this is intrinsic and how much is calibration. Absolute errors and systematic errors of these data points is tricky, and that creates problems if you want to do more advanced interpolation analysis methods across the blocks. So it's essentially, how much do you want to smooth this in order to make a movie or something like this? Here are, these are rotation measure maps of 3 different AGN. And see with rotation measure, there's even more issues related to the fact that any variations in the polarization sensitivity really hits you in rotation measure because you need all 3 frequencies. You need to protect the jet and all 3 frequencies to get a good rotation measure. So I've masked here are the pixels where that's not the case. You can also have wraps in the electrofractal position angle. So if you've got steep rotation measure, the VLBA is going to change dramatically, maybe more than 180 degrees if you lower the high frequency. So it's not going to be square fit. And then the same issue with the variability time scale. We don't quite know how fast the rotation measure is changing these sources. So this is why it's good to have somewhat slow jets in there to check. Okay, so I've not progressed to the level of making actual triple movies. So you'll see there's so many talks here, it's just a completely different. That can't be true. Okay, so the PH2 collaboration has been doing a lot of work on dynamical imaging. What I do with dynamical imaging is that you want to make reconstruct a movie from time source, which you know that each frame has intrinsic errors, but you want to impose some sort of conditions on the movie. But those conditions are varied in this objective function. So you've got a square term here, which is each frame for your movie should be consistent with VLBI data. Errors. We also want to demand image regularization function, which is related to things like entropy of the image, smoothness, this to be positive quantities. Then you can also impose frame-to-frame stability. So this is the concept of optical flow. And that's essentially smoothing those vectors of the pixels. And what this method does is you can actually solve for this and correct all of the errors of each image simultaneously in the data set. And it's also filling in the missing information using the proximity side and also using all the frequency information. So we've got a higher resolution image, and then have that more frequency with it, triple across. So the challenge is to pick the right regularization functions and weights that can handle those large absolute scaling errors in data and are appropriate for the variable time scale source you're looking at. Because you don't know a priori, say, how fast the polarization changes with the source, so if you model that in here. So that's work that's ongoing right now. And just to summarize, part of the ngEHT science case is understanding potential dynamics. That's going to require movies. There's a enormous PR potential here, but there are a lot of calibration issues. This project is being extremely data calibration intensive activity involving at least normal calibration. It's kept us busy during the pandemic. And, I think the dynamic ranging, this is will be a good first for us in calibration. There's enormous potential here in making movies that are a lot smoother. Ready. Okay, so I'll let that.
Sure. Any questions? Yeah. Yep.
Okay, yes. Very nice, man. I will identify future roles. That's fantastic. Let me ask you one thing. From how many of the sources are you detecting transfer gradients for this mission?
Yeah, it's a good question because I don't trust that they would have fully the calibration yet. I would say at least half show some signs. Yeah. But I don't want to give you an exact number.
Richard?
You made the point that I was trying to make myself. That was registration because images are
Yeah, it's very hard.
spectral index and rotation measurement are an entertainment. As a contribution. You do have 1543, and I don't know what your schedule is like. You're not forced the registration by transfer and calibration. 1543.
You mean line up features of 43?
No, the frequency phase transfer calibration.
Oh, using the calibration. What's this?
If they're scanned along by that.
So we do the 50 hertz scan, we rotate the receiver 24, we go to 43, and go to the next source. So it's not interleaved, it's not like phase referencing. So it's time scale would be the 43 gigahertz will come about, get this right, 5 minutes after the. It might be doable, but it's not so nice.
We changed the schedule. It went around 3 times. It'd be fun to play with, but you've got a lot to play with.
If you were sourcing, yeah, we were kind of pushing this. We had to optimize the number of sources.
So, I'm very interested in trying to understand what the implications would be in terms of survey strategy, et cetera, for integration. So it looks like for every source, you need a lot of prior data.
Yes.
To know the optimal sampling cadence.
Exactly, that's the point I wanted to make. You need that some guidance about what the ngEHT cadence should be. And that has to be from 86 gigahertz VLBI or 43.
Very quickly. So I saw your first selection criteria, the first point is the max threshold.
Yes.
So this will be rolling out in most of the isotopic quizzes. So I saw you have 2 in your set. One is Nahel, the other one is the other Nahel.
Oh, I can't remember.
All right, just for present, because I was curious, was the other one with max density higher than competence?
Yeah, it was. Just barely.
I see.
I'll tell you what it is after.
Any other question? No? Thanks again, Matryoshka. And now Antonio Fuentes is going to talk us about 3C279.
Okay. So yeah, most of you know have already seen the presentation a couple times. So, but I don't know. I think it would be nice to actually show again the owners of space VLBI and what can we achieve with the RadioAstron future missions and also the ngEHT. So okay, so I'm gonna talk about the result that we got with the RadioAstron observations and also the supporting Granada radio from 3 antennas scattered around the world here of 3C279. So this very famous source, you have already heard about this source many times in the meeting. Observations were performed on March 10th in 2014 at 1.3 centimeters, so 22 gigahertz, as I said, supported by 23 ground antennas. So you can see all the telescopes observing together with RadioAstron here on this figure. This is the UV coverage that we obtained with the ground array shown here, and then you can also see all the space baselines how they feel the UV coverage in this plot. And we achieved we could detect fringes up to 8 Earth diameter, which corresponds to an angular resolution of 57 microsecond. And you will see in a second that actually this, I mean, we don't have resolution in this direction, but actually we don't need that because the jet is pointing this way, so we have all the resolution that we need to resolve the transverse structure. So RadioAstron also has, I mean, the space interferometer also has polarization capability, so I will also show the polarization results. So this is what we got. This is the RadioAstron image, 22 gigahertz, but combined with the same beam that the one that the 7mm image from the VLBA view is around obtained for the closest time we got. So as you can see, the similarity of these two images is striking actually. Maybe we are seeing some optically effects here, but overall the two images are really consistent. But the question is actually, can we compare our observations with the ngEHT 1mm image, which is 3 years apart, but we are also, you know, we are actually interested in see if RadioAstron can actually compare with the ngEHT. So in order to show that, well, spoiler, okay, here it goes. So I played this movie in which I'm just, you know, decreasing the resolution of the beam until the actual resolution that we obtain with our methods, which is beamless. So yeah, the answer is yes. So thanks to the amazing resolution that RadioAstron provides, and also because the UV coverage is strategically located in this direction, so we can resolve the structure. We can compare with the ngEHT 1mm image, and also we can see all this animation that is also seen in the 7mm image. So this image is, you know, this is the whole picture. You can see here, the zooming, well, actually it's the zooming, but the comparison with 7mm. And this is linear polarization on top of total intensity. This is our total intensity image. Here we have all the RadioAstron contours with the 1mm image on top. So these two are at the same scale. You can see how actually the 1mm image is just the core region of all this huge piece that we see here. So this image, we obtained this image using the ngEHT imaging library. So this is not, your traditional clean image. This was performed with our methods. Probably this is the first time our methods are used to image space VLBI data. So now more people are starting to do it. So we have this paper by Thomas and also doing imaging of CA4 with ngEHT imaging, which he had also really nice results. So yeah, so in order to obtain this image, just a little bit information on how we do it. So we first image on the ground only data. So we flag all the baselines to RadioAstron, and we just with the image of the ground only, we take something similar to this here, and then we use this the ground only image as prior for imaging the whole thing. So then we added back the RadioAstron baseline, and then we perform the imaging again, first with closure only information, because so as you know, I mean, this is not something that will happen to the EHT, but in some other experiments, EVN experiments, or global VLBA experiments, sometimes antennas doesn't just antennas don't deliver the system temperature information, so you cannot really do a proper a priori calibration. And so, but since we have so many closure information, because we have 23 antennas and RadioAstron, we did a really good closure only image first, and then we set the predictor limits, solving the problems with the embryonic distribution, and then we just incorporate back the complex visibilities to the process and finalize the image. So I'm really actually proud of these plots here. This is the fitting of the user report to the data. This is the usual RAD plot here. These are amplitude spaces, and then we see here some closure phases, some closure amplitudes, and also some parametric phases. All of these plots have RadioAstron involved in the fitting. And you can see how well we can fit the longest baselines, the perigee imaging, everything actually. So it's a bit more tricky for polarization of the longest baselines, but you can see how the perigee imaging of RadioAstron actually can fit pretty well with the image. So as usual with our methods, we also perform a parameter survey to assess the robustness of the images with the different hyperparameters. So all of these images actually fit the data equally well than the other one that I showed. The other maybe just a little bit better, but actually all these images are at the same level. They are really consistent with each other. So actually, I mean, this image is more data-driven than regularization-driven. So since we have a lot of information, actually, regularization is not that really important. Yeah. So okay, how we compare with the EHT? So if we see actually, if we just draw these lines here, we see how actually we can recover a core, an elongated core that is consistent positional with the EHT. And if, although these are 3 years apart, we basically don't have to say much change, as we can see it here, although, this is we have some uncertainty here. If we just, align the images by the right user, we are not attempting any coercive gear analysis or anything. This is just a simple and quantitative alignment of the images. We can see how well the structure match, the core, and also this jet feature that we see here seems to also match the central filament that we see here. But as I said at the beginning, with the RadioAstron, the Granada array, we can also recover all these filamentary structure that extends 1 millisecond to the southwest. Yeah, so we see not only, we resolve the jet structure transversally, and we find these helical filaments that cross on top of each other. We see clearly 2 filaments, and possibly a third one, which is here, which is fainter. I'm not so sure about this one, but anyway, these 2 filaments, these 2 helical filaments are really well resolved. So yeah, so regarding the origin, the possible origin of this filamentary structure, so these filaments present a spatial periodicity of 175 parsecs in the relative distance. Yeah, so we have thought about the possibilities that the physical processes that can originate these filaments. So the session of the jet is actually discovered in the EHT paper due to lens steering effect of binary black hole system. Then processes, physical processes associated to the black hole of the ngEHT are also discovered because that implies superluminal propagation speeds around the filament. These filaments are not uncorrelated to the outer disk because that would imply accretion disk like one or two orders of magnitude larger than the usual accretion disk sizes. So the things that we have left is the development in instabilities, and within this we have current-driven instabilities and chemical instabilities. But since the jet is already fully accelerated in the core region, this is also a result from the EHT paper, then we are probably seeing chemical instabilities. So, within the chemical instability scenario, we have that elliptical modes can produce the observed chemical structures. If we also have a helical mode interfering with these elliptical modes, then we might be seeing also this might be causing also this third filament here. And we can, just do some analysis, some chemical instability analysis, and derive the weight length and the mole, the weight and the mole, and the weight velocity. And doing some calculations, we obtain a jet Mach number greater than 10, which indicates a kinetic intermediate flow. And this allows also to set an upper limit of 20 for the lowest factor of the source. So now, taking all this into account, and the beautiful limits I wrote, and all this information from the Helfond's instability analysis, we propose a new kind of novel model to explain the traveling components that are usually seen in 36279. So a bit of context here. So Marcel and here in just a few years ago, proposed that 3 years old. So they proposed this model in which the traveling components are shock waves traveling downstream of the jet. But actually, the estimated propagation speeds of the fitted components from this beautiful paper from Granada, from the kinematic zone, along a number of sources. So the propagation speed actually lower or equal than the inferred jet flow, that we estimate. So which is actually the shock scenario. So then if we take a look at this image, that we see that we have some regions with increased emissivity. So, based on all the previews, then we propose that these components that are identified with this brightest region in the filaments are produced by local changes in the fluid properties, like the velocity of the big angle. And actually, this Doppler boost emission in this region. So, actually, if you look at this image here, I mean, it's not so clear, but this is corresponds to the phase of these waves, and we just computed a kind of model in which we computed this perturbation, this spectral perturbation, and added the lipstick effects, projection effects, and everything. And then we realized that actually in those points, in the phases of those waves, the Doppler factor can increase by a factor of 1.5 or so, and that can actually explain the increase in the emission that we see in these regions. So then we propose that these local changes in the fluid properties within the filaments are actually the component that we see traveling. So as you can see here in this sketch, so the instability is being formed, and then we have this component, and as the instability develops and travels downstream of the jet, rotating, and also like moving, then we see the component moving forward, and new components being formed here. So yeah, we also have polarization, as I mentioned at the beginning. So a few properties of the polarization. So the source is mainly polarized with that indirect degree of polarization of around 10%. We see that the VLBA seems to follow the propagation direction of the jet, which indicates a strong toroidal component on the field. And also, if we look at this image, this dotted black line here indicates the main jet axis. Then if we just take a close look here, we see that most of the emission in the jet is located to this side of the jet. There's basically no bright emission here. So if we then look at the results that we obtained from RNC simulation of the prospect scale that are fed by helicomagnetic field, we see also that for small beam angles, the helicomagnetic field is causing also this asymmetry in the emission. So taking this into account and the strong asymmetry that we see here and the polarization properties, and also the stability analysis that we did before, we can infer a flow level factor of around 13, which is in excellent agreement with your stuff 17. We can also infer a helicomagnetic field that is rotating clockwise, and this would also imply an intrinsic pitch angle of 45 degrees, which Lorentz transformed to 86 degrees in the observer frame, which is also pretty in very good agreement with the strong toroidal component that we see for the Just to conclude the presentation, okay, so we know that the HT will observe all this in the emission. But why don't we just take this image, generate sensitivity data with the coverage of the UV, with the UV coverage of the ngEHT, And then we try to image and see if the increased sensitivity and increased dynamic range of the ngEHT can actually reproduce these results and see all this image. And I will just leave the summary here. Thank you.
Yeah, it's a great talk. I have you had a bullet on the previous slides that the EHT couldn't see the extended emission. Did you actually try to take your image and sample it with the EHT coverage and image it?
No, really.
Because in the paper they say they can't do it, but because some of these knots that you have here, I can't tell from the image how comparable they are in sort of total flux density to the main one up there, but they're of a distance that I could imagine the EHT possibly having substantial signal. They got ones they what 4-ish hundred microseconds away. The first one. Yeah, like that's a double. That's a ripple of about half of a gigalambda or so in the UV space. But I don't know, right?
Actually, well, this is kind of like on a scale. So
It's much fainter.
yeah, but actually, in linear scale, this two is not visible. So I guess the difference in brightness between these two shouldn't be like another different thing. So
It'd be interesting if you could just take a look at how the visibility data, like, look if you take your image and sample it with the EHT coverage, let alone ngEHT, which I think I agree with probably like all of this stuff.
I was involved in the imaging of physics 79, but I remember that some premium images also some filaments that connected the core and the jet, but I'm not sure how close they were.
I don't think the EHT would image this whole thing. I just think there could be signatures in some of these structures in the EHT data. No, I don't mean this field of view is accessible general. Yeah.
Sarah?
I should probably know this, but I don't. What's the constraints for the X-ray now on these? Because it's really interesting. If you can constrain the motions and the velocities, right? So you can make a really nice prediction for some of the variations over time in the high energy emission. And like, have you looked at any of these correlations or thought about it?
I don't know.
Okay, so I was just looking at some, I mean, I know there's archival data, but I just don't know if there's enough coverage, but it's something you could maybe think about going out.
Yeah.
So, with fractional optimization, you have fractional optimization up to 60%.
Yes.
So that is completely uniform. So, what is the Teresa fractional optimization?
Yeah, I wouldn't trust much those values. Actually, those values are only located at the edges of the total intensity map. So maybe this is just artifacts of the. This is not really. I mean, if you see, I mean, when we have some signal like the core or around here, the fraction polarization is 0.4. The core is actually pretty polarized. And these values are just outside of the, I mean, almost at the edge of the one intensity, and all it's just
Answer?
Question which only leaves my ignorance, but when you're using both products, if you have a strong delay across your pattern, as I understand it, that won't work. You then solve for phases. Space will be unlocked and have quite significant delays. You take that into account.
You mean doing free feeding and so on?
Show you the many phase errors.
I mean, I don't really know what to answer actually. So I can tell you the kind of because this started for also in the 3D imaging. The free speaking actually was pretty good. We got delays and resolution that were also depending on time. So it's like it's related to the acceleration of the spacecraft also near the key. Yeah, we took that into account when we did the calibration of the
Radio Astron people should take it. Well, let's see. Yeah.
Thanks again, Antonio. Last talk for today comes from Teresa Toscano about 3679 of RadioAstron.
Because you haven't had enough.
Oh, sorry.
This is enough, like pretty much. So I'll be continuing on 24. We've got the text level. So I'll be exploring the non-specific structure of 3679 with RadioAstron. So that includes some main points that I'm going to talk about. I'll be quick, so don't want to stand between you and the. So yeah, first of all, just a bit quick background that you already know about. A comparison with these observations, another comparison with VU and other each week to see that it's coherent and consistent. Then I'll explain a little bit the initial process, and finally I'll just summarize and say each sample top regarding each DNA. Right, so as you already know, later 3629 is quite well known as study source by history programs such as MOJAVE, ngEHT, VLBI as well. So why is this important? I mean, it's quite important because of this beautiful radio jet that we've got. It's quite powerful. And the importance of this project is that because it's the next step to the one that we just saw, that it would, like it's 4 years back, as I will see later, it will enable us to see time evolution of the maybe, and see how the magnetic field rotates and that will be enhanced, especially because of the filaments that we just saw. So in order to see that comparison, allow me to introduce a little bit again, Antonio's work. So you see, his data is from 2014, while the experiment we're currently working on is from 2014. Now, well, the good thing is that we have the same frequency, so we can't compare exactly the same results. Although, while there's 23 ground antennas, we just got routine these experiments, which is not the best, but we'll manage. And the resulting power will be affected by this, just reaching 15 microseconds. So you can see a comparison of few coverages. It's quite clear this is a bit cooler than the other one, but you see that in the end, the very preliminary results that we got are pretty consistent. So yeah, this is a comparison with a very preliminary image. Let me stress this. Compared with Antonio's image. So we can see some filaments here as already presented. And there is he's got 8 Earth diameter, which is a very elliptic orbit of the Astron. In our case, we get up until 12 Earth diameter. So that should be quite nice. And both images are around the each image. And we can see here that the structure is pretty much consistent, although I wouldn't say that we can't see filaments yet in the 2018 data. Right. So let's compare now with the VU and MOJAVE and ngEHT. So just like the points, the extended structure and the elongated matrix is to be consistent with that image. Also with how you can see here, extended structure and the matrix in there. Also, the phase pairs are not that bad, I would say, so it's pretty good considering all the factors. So we're quite proud of this image because even though it's very preliminary, it kind of goes in the right way. So other than this, we can also see the imaging process that's in the enclosure quantities. It's quite well fixed with the model and the orbit. So right, in the same way, similar fashion that 20 later, we got some problems with the temperature. So because of this, the calibration of the amplitude was a bit, let's put it gently, imperfect. And in order to use RadioAstron data, we have to first image the ground array, taking out all the RadioAstron baselines, image it, just using closure quantity because of this imperfect amplitude calibration. After that was the self-calibration, and that's when we introduced the complex visibilities, and finally the couple of other rounds of imaging. So we finally obtained this image. Now, like I said, this has better and not well. And so we're confident that we might be able to observe the filaments and the time of evolution of these filaments before this year. So, yes, you might be wondering now, why can't we see the filaments in the, even though it's very familiar? Well, first of all, it's a very variable source, 369. So, yeah, and also it's quite weak. Like the flux that we got, it goes from 20.
Seven.
Right?
27.
27 to 11.4 this is now later. So because of this very variability, you might not be able to see the filaments. Also, useful to coverage, so less ground stations, less sensitivity, less amount of coverage. Also, the calibration is not yet finished, so we're still working on it, for the amplitude of places, but also taking a lot of time with RadioAstron, because even though we get fringes up to 12 diameter, we're still working on it. And we also have to do parameter survey. If we just tried some parameters, you know, to obtain this image and show it to audience, but we're still working on it, so we'll expect to do that in a few minutes. So in summary, we have image is 209, 22 gigahertz, 15 microseconds, 24 grams, oh, sorry, 40, I wish it were 40 grams per minutes, and it's pretty consistent with all the data that we've seen so far. We expect to see the time evolution. I'm extremely excited because there is 2018 EHD data, and we're trying to get our hands on it and see if we can image that as well and compare, because as far as I know, it's just a few months apart. So it will be quite nice to have that reference to see how it has evolved as well. So yeah, these are very preliminary. There's always a margin for improvement, quite a lot in this case. I think we're just getting started. And for the future, we'll try to get calibration and the truth data. Also, visualization is useful. The results of continuous years. So we'll try to do similar function, same thing. Some model fixing maybe, structural interpretation measure as well, because we've got all the necessary tools for it. Finally, a lump survey and just a general proof of image and with all different approaches. So that being that, I'm open to suggestions, comments, or anything you want to add to it. Give me a second.
Yep.
I forgot that because not all the I was going to show you these preliminary results. While you're doing this, I'm just playing around with parameters. It turns out we found this. And so it was quite fine. We had a good laugh. Like, oh, we found an alien. I don't know, like a dementor of the Harry Potter man. So yeah, I just wanted to show you this. Yeah, I know. So yeah, we're extremely excited and also waiting for the NGHC to see if we can improve this resolution and get the results. So yeah, I'll just leave it here.
Okay. Tom.
Yeah, so this is the first one, great talk, Teresa. The coverage that you have here, UV coverage, and I guess this is similar for antenna as well. These RadioAstron coverages are so one-dimensional that I mean, have you this imaging something like this is so hard. Have you tried doing like just sort of more traditional VLBI interferometry, sort of plotting just the UV amplitude versus baseline length along the dimension that you have access to, and comparing that between these two? It's basically perpendicular to the jet you're looking at, and it should give you a sense of, you know, the projection slice theorem and all that. It should give you a sense of the sort of integrated flux profile in the image, and that you probably have covered really well in both of these. And you compare out to 4 or 5, whatever it is, extra lambda in yours versus that one. And I know the source is variable. I just, you know, visually compared these two things projected on the axis that you do have available. You asked for additional ideas, so I'm just wondering.
Yeah, no, I definitely have done that. But yeah, thank you for bringing it up because I'm got really curious about it. So I'll probably try to do that as well. Thank you.
Sarah?
Great talk today. Yeah, sort of building on what Dom was saying, I was wondering, you know, you have your theoretical models, is it possible to go in with a prior of a kind of semi-analytical propagation of the waves that you would expect where it is, and maybe you don't have a perfect image, but you can make some assessment of like how likely it is that this is, you know, the badly sampled image of a propagation, you know, like rule out the theory or prove it or something. I mean, is that something you guys are thinking about?
Yeah, we used a Gaussian pilot and the graduate, and then we used this graduate pilot in order to do the one with RadioAstron. So we learned it and we tried to constrain the image by that. But that's
Yeah, perhaps I mean, that's an excellent point. The two observations are 4 years apart, and these components they are produced by these stabilities of recharge. They are transparent and they evolve. They are not linear. So at some point you will see kilometers, and then you reach a breaking point, and then they will disappear, and then they into more streamlined, and then they develop again. So they, and then 4 years apart, it's very difficult.
Okay. So
But this is an
too long
excellent.
of a time.
This is an excellent point. Actually, we are investigating, but not compared to 4 years ago.
okay. I suppose it's better to just work with what we have instead of constraining it beforehand, so we're not biased, I suppose. But yeah.
Priya?
Quick question. Very nice one. So I was curious when you showed the compared images and so are these calibrated so that I can read it correctly and say that the spot has really brightened on the top, or is it too? Yeah, it is.
They are.
They're not comparable, right?
Yeah, and also keep in mind that this is really very.
Yeah, yeah. I
I-
should read anything. It's not yet comparable.
You check also the market views, you can still some small and not this.
I see.
So it's this has come basically the last few days.
Yes, no, in principle, it's not really comparable. I would like to know
What I'm really
really
tempted, right, those 3 knots that you see in the bottom there, they seem to have moved apart. Was that could be?
Yeah,
I don't want to go there yet.
Yeah, I know, I'm kind of like, we can see something there, but what is that?
Something that we have here for young people. We have here the person who actually developed a shopping model, which is professional. So we are really honored to be here and discuss this kind of things. And we were taking a look at these spots. That if you look at your images, and into the usual model fitting and the usual tracking time and so on, this is what we always have mentioned, that these are shopping demos, so there's a shop move around. But then
We want to show, I mean, I mentioned this is in my review.
Ah.
Sorry, I missed the other slide. You want to put the slides, my slides?
Because it says that it eliminates the shop model because the speed is slow.
Yeah, just here.
Yeah, I can see that.
Okay.
Which suggests that a dictation shop should be needed.
Antonio, which slide?
And the possibility is that when we see this, is that this is blind spot because actually there's a change in the orientation velocity along the filament, which means that in this case, it may be that some of these things that we are seeing here actually yeah, so it may be that actually they are just these filaments extending, moving out, and maybe they are not shops in that sense. That maybe this. So yeah,
They will get to come and you get to go. The father always something to yeah, nature does what nature wants to do, right? What we did is we're explaining the light curves, multi-frequency light curves with shops. But there are filaments that are doing this in some sort.
It depends. What is
That's up to
it?
nature.
What is the state? Is it empty state? Or it is
My feeling is that what we have seen is that there are some cases the source is very stable, and then somebody reaches one of these instability routines, and then develop these filaments, and then they break down, and then you come again to the usual filaments, and maybe that's a short comment actually appear absent of these filaments,
case you see shots on this side.
I'm interested to see if you could explain anything by magnetic reconnectors.
Yeah. So we are working on this one.
Perfect. Any other question for Teresa? No? Thank you very much again. Thank you. See you after the coffee break.
Care of your computer. What's going on now? Let's idea guys.
Yeah, it would be great.
Make sure it's on.
Excellent, excellent.
Just for the time.
Excellent. Okay.
Can you please delete my file because I realized I could not show the HT images.
Delete your file.
Yeah,
1 minute.
yeah.
Here.
No, this is the last one. Thanks. And then on the cloud, I
On
cannot
the
delete.
cloud, I cannot delete
It's
either.
error,
Only
right?
error.
Okay.
Yeah.
Okay. Here we have just plus accretion and it's only a discussion
Yeah, I guess so.
without slides.
Without slide. Excellent. Are we gonna
Did you stop recording? No. Yeah, please.
stop share?
Yeah, stop share and stop recording.
Share. Stop.